Hello, welcome to our channel for probability and statistics. In this video, we will talk about normal distribution and binomial distribution and the circumstance where normal distribution can be used to approximate binomial distribution. So we know normal distribution is a continuous probability distribution, and it is the most important and the most widely used distribution in statistics. Normal is also called Gaussian distribution, and its curve is bell-shaped, symmetric, and can be approximated, describe many phenomena in nature, industry, and research. So there are lots of examples, for example, meteorological experiments and rainfall studies and errors in scientific measurements that can be applied with normal distribution. And the very important example is that the sampling distribution of the mean is normal when the sample size is very large, or say larger than 30. So the mean of any random variables can be used with a normal distribution. So we call it sampling distribution. So normal density curve has this form with two parameters, mu for the mean and sigma standard deviation, and its square variance, sigma square, to measure the variance of the distribution. So any area, for example, the shaded area under the normal density curve represents the probability between the random variable, between this x1 and x2, this range. And its form is integral of the density curve over dx with the lower bound x1 and the upper bound x2. So when we calculate the normal distribution, usually we will transform the random variable x to minus mu and divided by sigma. So this is transformation called standardization. So this value Z has a normal distribution with 0 mean and variance 1. And this value is also can be checked from the normal table for the cumulative probability in the normal table. And next we will talk about binomial distribution. It comes from so-called Bernoulli process. So Bernoulli process is actually a process with the result binary. So the result will be a success or failure. So, but each trial in the Bernoulli experiment has a success rate called P, and this success rate remains constant from trial to trial. So each trial is independent from the other trials in this experiment. So this is the Bernoulli process. And the number of x of success, so how many times of success in n Bernoulli trials, is called a binomial random variable. So its distribution is a discrete random variable distribution called BXMP. So which means the probability of x success during n trials with constant success rate P. And it's the form, the probability distribution has a form is combination nx times p's x power times q's n minus x power, where q equals 1 minus p. So for example, in this example, n is 3 and p is 1 of 4. So for x, possible value is 0, 1, 2, 3. Each x has the binomial probability distribution equals combination of 3x, then times 1 of 4's x power, then times 3 of 4's 3 minus x power. And the calculation of the probability for the binomial distribution also can be checked from the binomial distribution table. And the normal distribution can be used as a good approximation to a discrete distribution when the latter takes on a symmetrical bell shape. So when the binomial distribution is not bell-shaped usually, but sometimes when n very large and the p constant rate is not very close to 0 or 1. We know the p is between 0 and 1, but if it is not very close to 0 and 1, for example, it's about 0.6, so and n is very large. In this case, we can use normal distribution to approximate a binomial distribution because normal distribution is much easier to be used or can be used to do some statistical testing. It is a continuous distribution, but binomial is a discrete. So if we use a continuous distribution to approximate a discrete, this continuous distribution can be used to do test, normal test, right? So it is more widely used binomial. So when a case n is large and p is not extremely close to 0 or 1, so we can use normal distribution to approximate a binomial distribution. So for the binomial distributions, mean is np, right? So we can use x minus np divided by binomial distribution's variance take square root. So transform to a z value, right? So just look it as a normal distribution with mean equals np and variance np cubed. So this z will approximately as a standard normal distribution. So it's 0 mean and standard deviation 1. And remember that Poisson distribution, which is another discrete random distribution, can also be approximate a binomial probability. So when np, n is large and p is very close to 0 or 1. So binomial distribution can be approximated by other distribution. So when n is large and p is not very close to 0 or 1, so it can be approximated by normal distribution. But when p is very close to 0 or 1, in this case, we can use Poisson distribution. So Poisson distribution measures the occurrence is not very often. In this example, not very often, not infrequently occurred events. This is Poisson distribution. So we just make some extra notes with red color here. So to illustrate the normal approximation to the binomial distribution, so we can first draw, for example, a binomial distribution with a histogram for different possible value, discrete value, 0, 1, 2, 3, 4, and so on, right? Then we superimpose a particular normal curve, which is approximation normal curve with the same mean and variance on this histogram. So you can see the shape between this discrete histogram and this continuous normal curve, they matches quite good, right? So here, the mu np 6 and sigma square np cube 3.6. And upon these values, we can calculate, for example, if we use binomials discrete, probability for random variable equals 4 equals the binomial of 4, 15, 12 with the constant rate 0.4. So this discrete probability is about 0.1268. But if we use a normal approximation, we will calculate x equals 4, which approximately equal probability of x between 3.5 and 4.5, right? Then we transform this value to the z value is about probability of z between these two values. So from the normal table, we can get about 0.1214. Though this value is quite close, lower than about 1 to 3, 2%, right? Thanks for watching.